I'm going to finish off black holes. We won't get to the Kerr metric, and we'll just finish with Schwarzschild, and then I'll talk a little bit about cosmology. So just to recap, we studied light rays going into a black hole in Schwarzschild coordinates, and we found that these ingoing light rays sort of diverged off to t equals infinity, and did this. This created some puzzles because inward-going radius was future-going time for such light rays. But then we considered light rays which were which would be future-pointing light rays, but of the other type. Okay, there are obviously two independent coordinates, and unfortunately, these guys were going backwards in time outside the black hole, and so there's a sort of inconsistency in this picture. So and I pointed at the resolution, which is to introduce new patches of space-time where there will turn out to be two copies of the interior and two copies of the exterior. And we're going to see this now. So we're going to put this all together. By defining U to be T minus R minus RS log R over RS minus 1, and V to be T plus R plus RS log R over RS minus 1. And so U is constant for outgoing null rays, and V is constant for ingoing null rays. And then, so the person who did this was Kruskal, Martin Kruskal. He later became famous in integrability, theory of integrable systems. And so its physical review 119 1743 in 1960. And so Kruskal said, okay, well, these are good coordinates, so let me change the whole metric to these coordinates. And so we have we have du equals dt minus dr over 1 minus rs over r, and dv equals dt plus dr 1 minus rs over r. Okay, just by differentiating the log. And so the line element is equal to minus 1 minus rs over r du dv plus r squared d omega squared. Okay, so it doesn't look so different. than it did in the ingoing or the outgoing coordinates. It has no du squared term. It has no dv squared term. It has only the off-diagonal term here and here. So 0 on the diagonal in the sort of T and R entries, or U and V entries. It only has the GUV. And R, so this is a funny formula because it involves R. Of course, U and V are the coordinates, so we have to express R in terms of U and V. R is defined by R plus RS log R over RS minus 1 equals V minus U over 2, right? If I take V minus U over 2, I get 2R from here, and I get twice the log. So divide by 2, and I get this formula, i.e. R over RS minus 1 multiplied by E to the R over RS is equal to E to the V minus U over 2RS. Okay, so this is right-hand side is some function of U and V. The left-hand side defines R. Okay? Now, clearly, this is only valid for R bigger than RS. Okay? As were the original formulae. I mean, the log would have an imaginary piece if R was less than RS. So basically what we're doing is we're sitting outside the black hole, and we're changing coordinates to some new coordinates. And the coordinate transformation is completely valid here. Nothing wrong with it. But the coordinate transformation is fishy at R equals RS. And as I explained, we need to do something fishy to remove the badness in the coordinates. Okay, so we're doing this outside RS. We're going to go to these new coordinates, and then miraculously we'll discover that in the new coordinates there is nothing wrong at all at R equals RS. Okay, so if you graph this, okay, in fact, you'll see the left-hand side. If I graph this function as a function of R over RS, obviously at large R, it grows exponentially, right, like R e to the R. At R equals 1, it's 0. And at R over RS equals 1, it's 0. And R smaller than RS, it's negative. Okay, so the left-hand side is negative for R less than RS. This side is always positive. So this doesn't really make sense for R less than RS, but, you know, no worries. We're just changing coordinates outside the black hole. Fine. So this is our metric, okay, in these new coordinates where R is defined. So this defines R. Oops. This defines R of U and V. Okay, so now I want to re-express this. I'd like to simplify this metric. So what I'm going to do is use this formula to calculate that factor. All right, so let's call it star. Okay, so star implies, so if I just take star and multiply it by RS over R, what I get is that 1 minus RS over R is equal to e to the minus R over RS times e to the minus V over e minus U over 2. Okay, so it follows that ds squared is equal to minus rs over r. Sorry, there's a rs over r here. Rs over r minus rs over r times e to the minus r over rs times e to the v minus u over 2 rs du dv plus r squared d omega squared. Okay, so that factor multiplying the du dv is completely positive now. Okay? You can sort of see what we're trying to do, which is avoid sign changes in this term. Okay, so we've manipulated around so that that factor just doesn't change sign as I go across Rs. In this form, it obviously does change sign. Okay, then I did this coordinate transformation to this form where it's not going to change sign. Okay, as I've emphasized, the coordinate transformation only makes sense if R is bigger than Rs. And now we do the really tricky part, which is we set capital U equal to Rs e to the minus little u over 2Rs, and capital V equals to Rs e to the v over 2Rs. And why is this tricky? Because the right-hand side is totally positive. The left-hand side I'm going to extrapolate to negative capital U and capital V. Okay? And so what happens is that ds squared, so these are positive, but these we're going to extrapolate to negative values. Okay? And actually what we're doing here is analytic continuation. Okay? We're really using the fact that in the right set of coordinates, the metric is analytic, and there is a unique analytic extension. Analytic in the complex number sense. There's a unique analytic extension of the metric to negative values. There is a unique analytic extension okay, so we have u and v. Then ds squared becomes 4 rs over r. You see the du is just going to give me a minus du over 2. And the dv will give me plus dv over 2 times this factor. So here we have e to the minus r over rs du dv plus r squared d omega squared. And now, finally, we're going to set u equal to x minus t and v equals to x plus t. And so ds squared is equal to 4 rs over r e to the minus r over rs. This factor is singular, but only at the center of the black hole. R equals 0. We know that's a real singularity. It's positive everywhere else. Minus dt squared plus dx squared. This looks like Minkowski space. Plus r squared d omega squared. Where x squared minus t squared is equal to uv is equal to rs squared e to the v minus u over 2rs is equal to rs squared e to the r over rs times r over rs minus 1, this equation defines r. Okay, so I have this metric, and r is really a function of t and x. And that function is defined by this equation. And so you'll see in this equation that you see in this equation, the left-hand side and the right-hand side can both be positive and negative, and therefore we're going to fill out most of the xt plane. Okay, most, actually not all the xt plane, but most of it. And similarly, t is u plus v over 2 equals rs log v over u equals rs log x plus t over x minus t defines, well, we don't, we don't need t for the metric. Metric doesn't depend on little t. But that's just a relationship between our old original Schwarzschild time coordinate and this new coordinate. And I'll just put in brackets here. We'll need to correct this slightly momentarily. Doesn't really matter for the metric, but you can see the problem, which is that when x minus t goes negative, well, when either the numerator or the denominator go negative, that log is going to have an imaginary part, and we'll see we'll have to correct that. So that is the metric in Kruskal coordinates. Okay, where this equation defines r. And amusingly, this formula is wrong in Bob Wald's book, which is one of the famous textbooks on GR. But if you look at this carefully, it's not right. It's a great, Wald's book is a good book, but it's very formal and, not quite right in some things. So let's try and understand what this means. First of all, if we look at this equation for r, as I mentioned, so that the two key points. One, what happened to the singularity at r equals 0? Okay, so there's a singular at r equals 0. Now, so obviously the metric is singular when r is 0, but we're using these x and t coordinates. So what is the locus of the singularity in the xt coordinates? Well, I just come to this equation and put r equals 0. So this factor is 1, and this factor is minus 1. So this means i.e. On the locus, a locus is like a line in the xt plane. On the locus, t squared minus x squared equals rs squared. Okay, because x squared minus t squared is minus rs squared, so I've just rewritten it this way. That's a hyperbola, okay, in the tx plane. So the singularity, which used to be at a point, is now a line in these xt coordinates, i.e. a hyperbola. And the solution is only valid, so it's singular, and it's only valid for r bigger than 0, i.e. t squared minus x squared. So this function here is, let me see, is always bigger than minus rs squared for r bigger than 0. So this is t squared minus x squared is less than rs squared. Okay, so there's basically an upper bound on this. There's an upper bound on this quantity. So x equals 0, t, the capital T, is going to have a limit. And basically, that's when you hit the singularity at some value of t. The second key point, is there a question? Was there a question? No questions? Okay, second key point, t doesn't seem to make sense. T only makes sense for r less than rs if we define it via dt equals, via t equals, and then we put an absolute value in the log. X plus t over x minus t. Okay, then at least t is real for all allowed values of x and t. As I said, little t doesn't enter in the metric, so it doesn't really matter. This is just trying to relate capital N x and little and capital T to little t, the original Schwarzschild coordinates. Okay, so now let's make a picture of this metric, of this space-time, I should say. And it's called the maximal extension Kruskal picture of a black hole, also known as the maximal extension of Schwarzschild. So we're going to be using capital T and capital X as our coordinates. So here's capital T, and that's capital X. And so the first thing we should plot, well, you can see what radial light rays do in these coordinates, right? Because radial light rays have, this term is 0. And so for radial light rays, x is plus or minus t, right? ds squared is 0 if dx is plus or minus dt. So a nice feature of these Kruskal coordinates is that radial light rays move in straight lines at 45 degrees. So we can draw those right away. Okay, so this is, let's draw the light rays through x and t equals 0. Okay, so this line is obviously t equals x, and this one, or maybe I'll write it as, what have I called these arguments, x and t? Yeah, so x equals t, and x equals minus t, or t equals minus x. And so, yeah, let's begin by figuring out where r equals rs is. So at r equals rs, well, those are the two lines that I drew, right? R equals rs is x equals plus or minus t. So we can just write down here r equals rs. This is r equals rs. So right away you see there are two versions of rs. Radius equals rs, not one. Secondly, let's figure out where the singularity is. So the singularity is along that curve. That's a hyperbole. There are two hyperbola. There are two parts of it. One of them is up here. Okay, so let's do that in a different color. This is a singularity. There's another part, another branch of the hyperbola down here. Okay, and this part of the space-time doesn't. That's r less than 0. Okay, so this is r equals 0. This is r equals 0. This is the singularity. So we don't know how to go beyond there using GR. It's interesting to ask, what about t, this little t? Obviously, this little t, if x tends to, if x is greater, capital X is greater than capital T and positive, and x tends to capital T, you see the argument of the log is going to go to infinity, so little t will go to infinity, right? As you approach this line, t, so this line is actually t equals infinity, plus infinity. And conversely, if capital X goes to minus t, capital T, then the numerator goes to 0, so the log goes to minus infinity. So this line is t equals minus infinity, r equals rs. And the same here. This is t equals plus infinity, r equals rs, t equals minus infinity. And now we're beginning to see the funny things about going backwards in time, okay? Because the t-coordinate advances this way on this half of the space-time, and it advances that way on this part of the space-time. And hopefully now, everything should be absolutely clear. Because when we send in an ingoing null ray, it just goes at 45 degrees in these coordinates. And so it just goes into the black hole and hits a singularity. Okay, but there was another copy of it, which is still ingoing, which comes out of this singularity, okay, and goes off that way. So those were our two different versions of the ingoing null geodesics. And likewise, the outgoing ones have exactly the opposite. There's an outgoing one which comes from the singularity and goes out. And there's an outgoing one which comes from infinity in this part of the space-time and falls in and hits the singularity there. So those are our two copies of the ingoing and outgoing null rays. And they were telling us that, yes, there really are two exteriors of the black hole. This is an infinite universe out here, right? And there's another infinite universe out here. Now, you can immediately see this universe cannot communicate with that universe at all, right? Because this universe can only send signals either into the black hole or out to infinity. I mean, if I'm sitting here in this universe and I try to communicate with that universe, the best I can do is to send a light ray like this, but it's just going to fall in the black hole. Okay, so it's impossible. These two universes do not communicate. Nevertheless, it's pretty bothersome, this, because you see, if this picture was really valid, you would say, when we sit out here, a long way from the black hole, when we look back, we can see the singularity of the black hole. Now, we have no clue what the right physics is at the singularity. The theory just falls apart there. And so basically, we wouldn't be able to predict anything. But this is not what happens in the real universe. In the real universe, this singularity is masked from us by the following fact, that when you have a collapsing star, so as far as we know, black holes form from collapsing stars, and when you have a collapsing star, it's, if you think about its surface, the Schwarzschild metric is only valid outside that surface, right? Inside the surface, you've got to take into account the matter. So anything that happens inside the star at smaller radii is going to be affected by the stress energy, so our calculation doesn't apply. I mean, you have to do another calculation. And when you do, what you discover is that inside the star, it's not Schwarzschild, it's perfectly regular, okay? So this is a surface of a collapsing star. Okay, so the idea is I'm going to give you some regular initial conditions, just some space with a star in the middle of it, but there's no singularities anywhere. And inside the star, there's none of this stuff. There's no singularity. Nevertheless, the Schwarzschild metric is valid outside the star. When you follow the star collapse, the surface of the star has particles, and they are massive particles, and they have to follow a time-like trajectory. In fact, they have to follow a geodesic, because just imagine an atom on the surface of the star, which is very weakly coupled to everything else. It's falling in under gravity. And so certainly this is a reasonable possibility, is that there's particles on the surface of the star. The only thing which would stop it would be pressure, which would hold them out even more. So the most they will do is fall in as if they were geodesics or in a Schwarzschild spacetime. So these guys will fall in and hit the singularity. Okay, there's nothing they can do, because once they're across this horizon, they cannot, they have to move within the light cone. Okay, they're time-like geodesics, have to go less than the speed of light. And so there's no way they can avoid hitting the singularity. So what it means is that in a realistic collapsing star, the picture is as follows. You have to use another metric inside it. You can use the Schwarzschild metric outside it. And particles that fall in on the surface of the star would hit the singularity. But notice that there's a lot of the singularity outside the star. And so, and you can use pure GR without stress energy in that region. So this part of the space-time is really there. I mean, it's really valid. If a star falls inside its horizon, it's a Schwarzschild radius, 2 gm over c squared. So if its outer radius becomes smaller than 2 gm over c squared, you'll get a diagram like this. And as you track the space-time inside that Schwarzschild radius, you're going to find that outside the star, there's a singularity, exactly the one we've described in the Schwarzschild metric. It is space-like. Notice the singularity is space-like. As I said, it's not a point. It's actually a surface. Okay, and so any particle which falls in, just outside the star is going to hit that singularity, and so there's huge. Well, it's just true that any ingoing. I can extrapolate this picture off to infinity, right? So this diagram goes off to infinity. The singularity goes off to infinity. So imagine the star is collapsed and I'm sitting way out here, but I'm just following a geodesic, right? That means that I put a particle here, there's a black hole over in the Andromeda galaxy, and I put this particle here. Eventually it's just going to fall in radially, and what that means is it's going to hit the singularity. So this black hole in an asymptotically flat space, right? If we really, this is asymptotically flat. It goes to Minkowski space. Black hole in asymptotically flat space will suck everything into it. Okay, are there any questions about that? Yeah.
I don't know if this is a silly question, but if we take these coordinates at face value, you say there's 2 copies
of space-time.
Yeah.
Which,
as far as the stuff in them, as far as their overall geometry are the same, but as far as the stuff in them might
be totally different.
And you said they can't communicate, but that's only true outside of the Schwarzschild. So like if I were to fall into a black hole on some kind of suicide mission,
yes,
I would all of a sudden be interacting with, for the 10 to the minus 5 seconds or whatever I've got.
That's correct. That's absolutely, it's a good point. So I fall into the black hole and I can see the other universe, right? So you will have 10 seconds of total enlightenment, total enlightenment, okay? You fall in the black hole and, ooh, there's a whole universe out there, okay? Crunch. That's right. That's correct. So, yeah, an astronaut falling in.
How seriously do people take that?
Well, it's interesting. Okay, so people study this in great detail. When I was about 20 years ago, I went to a conference and I was talking about some cosmic strings, and because I was one of the pioneers of exploring, consequences of grand unified theories and things like cosmic strings. And I gave a talk about this, and I was very clear, these are very speculative ideas. We'd love to test them, prove the theory's wrong, and this was great fun. But Chandrasekhar was in the audience. So Chandrasekhar was probably the sort of most powerful math person, partial derivative expert of the 20th century. And Chandrasekhar just did these horrendously complicated calculations that nobody else could even attempt. And he discovered the Chandrasekhar limit on the mass of a compact star, which is a degenerate Fermi gas. But he did millions of other things, and he understood the Kerr metric and studied in huge detail. His books are almost unreadable because the equations just go on for pages and pages and pages and pages, okay? And didn't bother him at all that an equation would include, 200 terms. It was just fine. So very brave guy. But he said to me, why are you thinking about all these speculative ideas? We have a theory. We know it's right. Even if these space-times don't exist in nature, they are right. Okay? And it's much more interesting. So he spent the later part of his life actually just exploring weird spacetimes in GR. And he said, look, they exist. I don't care about nature. This is the correct theory. And, these things exist. So it's a funny point of view. I never understood it, but I kind of understood what he meant. So you feel that by working on it, you're working on something lasting, right? Even if it doesn't exist in nature. And there's a fundamental paradox. I mean, the usual picture is that what came out of the Big Bang had no black holes. Okay, for some reason we don't understand. It was smooth. Okay, and there really is no fundamental understanding of that at all, certainly not from inflation, despite claims that people just assume there were no black holes at the Big Bang. Then all the black holes formed subsequently by collapsing stars. Okay, so that's the scenario, but it's very strange because there is this possibility of these other solutions which don't exist just more or less by fiat because we didn't allow them in the initial conditions of the universe. So that's I think that's a sign that we're missing something very important. I mean, the theory should exclude those solutions, and we don't really have good arguments for doing that. Yeah.
So, well, this is more of a question of your opinion on this, but how seriously do you take Penrose's wild character hypothesis in explaining exactly that?
Yeah, that was one of the motivations. So Penrose made a conjecture that initial singularities should have the Weyl tensor going to 0 as you approach the singularity. So he wanted to literally put in an arrow of time into GR, which would just exclude this kind of singularity by hand. So he wants to exclude this guy because at this singularity, the Riemann tensor diverges, the Weyl tensor diverges, but we could exclude it with that condition. So this is the Weyl curvature hypothesis. Yeah.
I just want to clarify the statement that you made sort of with the extra lines and stuff. So,
with the blue line?
Yeah. So
Okay.
The blue line you're drawing there is
The surface of the star. So what I'm saying is that imagine I've got a star which is collapsing. Inside the star, none of my arguments are valid. I need to resolve Einstein's equations with matter, which you can do. You can do it. It's messy. It's complicated. That's what Oppenheimer did. Okay.
related to the Schwarzschild radius.
Sorry?
How is that related to the Schwarzschild?
Oh, the Schwarzschild radius is this line, right?
It's okay.
So basically, the star is shrinking in radius, and if it crosses its Schwarzschild radius, so the Schwarzschild radius is just given by 2gm over c squared. So imagine the star is collapsing, but its exterior radius is bigger than this number. Okay, this is not very dense. As it collapses, the mass remains the same. So it's collapsing with the same mass, but the radius is shrinking. And when the radius falls below Rs, that is the moment the star crosses its Schwarzschild radius. Okay? Now, as I said, all this stuff, the metric inside here shouldn't believe, because it's smoothed out by the presence of matter in the star. I mean, you just solve different equations, and there's no singularity inside the star. However, if I follow a particle just outside the star, it really has to evolve in the Schwarzschild metric. I mean, it's a unique metric with spherical symmetry. So a particle just outside the star is going to fall in, it's going to cross the Schwarzschild radius, and going to hit the singularity. There's nothing matter can do to stop that happening. So it's a fundamental breakdown in our picture of space-time.
So are you saying that we can glue together solutions to the Einstein equation in like a reasonable way?
Absolutely. Absolutely. Yeah. So this is what Oppenheimer and Volkoff did. Oppenheimer did this just before he became director of the Manhattan Project. Okay. What?
Did you give a reference for this?
Oppenheimer, Volkoff?
Sure.
Oh, yes.
Is that the original paper?
Yeah, that's very standard. In fact, if you look in the little blue book, it's all in there. Did I bring it? I'll tell you where it is. Yeah, it's in They begin this. I'm not sure. Interior solution. Yeah. So if you look in chapter 21, it's called Interior Solutions. And the third section is the Oppenheimer-Volkoff equation. And it basically tells you if you have some... so this interior is Oppenheimer-Volkoff. Yeah, go ahead.
Does the parallel universe still exist when you have a collapsing star?
No.
It's not part of the solution anymore.
Well, no, because in this solution, let me see how it goes. You see, the meaning of r, this radial coordinate, is in this picture is all to do with the Schwarzschild solution, right? But when I do Oppenheimer-Volkoff, you know, r will go to 0 here. I have the surface of a star, and when I extrapolate the solution, you know, I'll go to r equals 0, and everything will be regular. So basically, this line gets replaced by radius 0, but there's no extension, there's no singularity, there's nothing. Okay, but nevertheless, it is true that this part of the space-time, there's nothing you can do to change that. You're stuck with it. Yeah.
It looks like if I just put something static that doesn't change spatially, it's going to find its way into the singularity. Is that true?
Well, you see, no, it is true, but only if this d omega is 0. Right, so throughout, we've only considered radial trajectories. Okay, so if there's a black hole sitting there, I can easily avoid it just by having a bit of angular momentum. But if I have no angular momentum, what can I do but fall in? So that's why if I have a black hole sitting there and I have a particle a long way away, static, so it has no angular momentum, eventually it's going to fall into a black hole and fall through the horizon. So this black hole does affect things all the way to infinity. I mean, because they will ultimately fall in and they hit the singularity. But only if they have no angular momentum. Yeah. Okay, so yeah, this is a great hypothesis, but it's totally ad hoc. It's just saying something we don't like in the theory, so let's assume it's not there. I don't think it's very satisfactory. It's distinguishing the future from the past. I mean, why? No explanation. So, what is interesting, I mean, as you probably know, I developed a cyclic model of the universe. And the cyclic model of the universe attempts to explain what happened before space-like singularities. And there are very strong connections with this hypothesis, that basically there's an attractor mechanism which takes the universe towards zero Weyl tensor in that scenario. So it's more of a dynamical explanation. Great. So let me just briefly mention what people's viewpoints are currently about that singularity. So current ideas. Maybe let me just emphasize. You cannot avoid the singularity through the effect of T mu nu. Outside a collapsing star, which falls through its Schwarzschild radius. And this implies there really is a catastrophe for GR. GR cannot be the final theory of gravity, and Einstein realized that. You've got to go beyond it. Many, many examples in physics where there's a really good theory, but it breaks down at some level. And a simple example is fluid dynamics, where you have the Navier-Stokes equations. And engineers use these to describe aerodynamics or motion of ships through water or whatever. I mean, these are wonderful equations, but if you make a shock, the equations break down. The density, the basic assumption of the Navier-Stokes equation is the density is a smooth function of the spatial coordinates. But what happens as a shock is that instead the density changes like that, discontinuously, and this shock moves at some speed, velocity bigger than the speed of sound. And that's what happens when an aeroplane goes faster than Mach 1. You get a shock wave, and Navier-Stokes breaks down. And what you need is a microscopic theory of air. I mean, there's nothing wrong physically. It's just that air is made out of atoms and molecules. And you need to describe the shock in terms of those elementary constituents. And so all this is another indication that GR is an incomplete theory, and you need a microscopic theory of the degrees of freedom in GR. There were ideas that string theory would be that solution. String theory sort of is, people hope, because the degrees of freedom are delocalized. They're not point particles, but they're extended strings. That seems to help. There are indications that string theory is better at dealing with singularities. There are newer ideas of entanglement, that space-time is not, space-time is only a classical notion, and that space-time is related to quantum entanglement of many-body systems. And I think those are very exciting ideas, that there may be a more elementary description of space-time than there is in GR. This sounds a good idea because the Big Bang is precisely the point where all of space disappears. Okay? That doesn't make any sense at all in GR. The metric becomes completely degenerate and singular, and the Riemann curvature is infinity, and everything goes wrong. But if you had a theory in which the elementary degrees of freedom were not the metric, but were some unitary quantum spin system, for example, and especially if it was a conformally invariant system, then it wouldn't care about the size of space-time, and it would be equally valid at the singularity. So that's my belief, is that that's what we're looking for. We're looking for some description of gravity which goes beyond the metric and replaces the metric with some elementary quantum degrees of freedom. And hopefully that will resolve these problems. We're going to do cosmology in half an hour. It's going to be tough, but I'll try. You see, the great thing about cosmology, we're outside black holes, right? So this surface of the black hole is called a horizon. I should have said that. Okay, this is a horizon. Okay, the definition of a horizon, it's some surface in space-time which, if I go within it, I cannot communicate with somebody outside of it. Okay, so here's the surface, and if I'm sitting in here, I can't communicate. Now, there's no signpost, you see, at the horizon. If I'm an astronomer and I fall through the horizon, I won't see anything happen at all. The Riemann curvature is small, I'm just falling in. No signpost at all. But signals I send will never make it to infinity if I'm across the horizon. So the horizon is a property of the global space-time. You need to know what's going on at infinity in order to say whether you can or can't communicate with it. So we are outside black hole horizons. There's a black hole in the middle of our galaxy. It now seems that almost every galaxy has a black hole in the middle of it. And there are many other black holes orbiting galaxies as well. So the universe is full of black holes. Deep, deep paradox for physics, because they've all got this singularity. We have no idea what happens there. Okay? But we're outside the horizon. The strange thing is the discovery of dark energy, okay, the cosmological constant, creates another horizon. It's a horizon beyond which we can't see. We're inside that horizon, okay? So we're outside the black hole horizons, inside the other horizons. And in a way, just that fact tells you there's a danger of a multiverse, okay? Because in the standard cosmology, there's stuff beyond this dark energy horizon, which we will never see, okay? Because the universe has begun to accelerate its expansion, and we're never going to see the rest of the universe. Wait till eternity. You will never see it. Well, what's it doing there in the theory? Why is it there? Is it there? Certainly, this cannot be a quantum theory, because in a quantum theory, all states, more or less the definition of a unitary quantum theory is that all states are involved in the evolution. You cannot separate off some sets of states in a quantum theory and have them do their own thing and not communicate with the other states. Because quantum tunneling allows all states to communicate with each other. So just this fact alone means that there's something wrong, in my opinion, with GR on large scales as well as on small scales, and it's rather similar to the problem on small scales. And I think a good theory of the universe is going to explain that what's beyond our horizon, the one we are inside of, okay, the horizon of the universe, what's beyond that is really space-time foam. It's quantum space-time foam. It's not a real universe. Okay, so this is a very radical opinion, I warn you, but I'm sure it is correct. So, okay, so now we're going to do cosmology. Only quickly. If you are keen, I might give you some more lectures on cosmology later in the year. I can't possibly do justice to it because cosmology is the biggest subject in physics, because it includes everything else in physics. Yes?
I'm sorry if this is really stupid, but how do we know that we're not in a normal matter black hole?
What do you mean by normal matter black hole?
Well, maybe I was wrong, but I thought you were just saying that we were in the horizon of the dark matter.
Yes.
Black hole. So
well, it's not a black hole, it's de Sitter space. So de Sitter space is a solution of the Einstein equations with vacuum energy, and it's an exponentially expanding solution. And in that solution, if somebody sends a light ray towards you from sufficiently far away, it will never reach you. So you cannot see part of the universe in de Sitter space. So it's similar to a black hole only in the sense it has a horizon. That's all. But it's a horizon we are inside rather than outside. Okay? Equally paradoxical, in fact, more paradoxical. De Sitter space is this amazing space-time. I mean, it's actually the simplest space-time in general relativity, apart from Minkowski space. In many ways, it's simpler than Minkowski space because it has finite spatial sections. I'll deal with it in a moment. You'll see. Yeah.
You were saying before that there's this one space-time foam outside
Yes.
But don't we have like stars that are really far away from us and leave our event horizon at some point?
Yes, we do. So in fact, any galaxy which is not gravitationally bound to us, if we follow it forward in time, so it's receding from us now, and we go far enough forward in time, it's going to leave the horizon. and it'll be like the astronaut falling on the black hole. It will go redder and redder and redder and disappear from view. So that's right. So my claim is that as that happens, that galaxy is dissolving into space-time foam. It's obviously right. I mean, how could this be wrong?
Yeah. Why do you say we're inside that horizon? It seems very similar to a black hole horizon. If we are outside, because the light rays emitted from inside the black hole horizon will never reach us, and the light rays emitted from an observer far away will also never reach us.
All right, you're forcing me to explain, which is good. I'll draw the space-time diagram. Okay, now the way to describe these causal properties of space-time are Penrose diagrams. I haven't taught you those, but I'm just going to draw them. In Penrose diagram, basically what you do is, say, for example, take Kruskal. You do a conformal transformation, which is a rescaling of the metric, to bring everything in to finite distance. But you leave light rays going at 45 degrees, as in Kruskal. And so Minkowski space looks like this. This is explained in Carroll, for example. Minkowski looks like this. That these are plus infinity and minus infinity. So when you do this transformation, so the Penrose diagram of Minkowski space, I sit here and I can send a light wave off to infinity. Or somebody in my past can send a light signal to me. Everybody is in communication.
Is this similar to the Riemann speed?
No. No. There's a past infinity light cone which intersects with a future infinity light cone. Okay. So Kruskal is quite different. Kruskal looks like, Kruskal looks like this. This is the singularity. This is the singularity. So this Penrose transformation has flattened that space-like singularity into a line and brought these infinities in. So this is kind of like, this is asymptotically like the Minkowski infinity. And then there's another Minkowski infinity out here. And the singularities inside the black and the white hole. De Sitter, which is the solution of the Einstein equations with only vacuum energy, looks like this. It's completely non-singular, okay? But it has a future space-like infinity. And this is a past infinity. And then my statement that you can't see part of the universe means that if I'm sitting here and going up this line, all I can see is the stuff in half of the space-time, right? There's a whole region here which I can never see. And this is the horizon, of course. This is the horizon in... Minkowski space has no horizons. You can see everything. The Kruskal has two horizons, and De Sitter has a horizon, a single horizon. And we live inside here, and all this other stuff, so there's some galaxy going along here. As we discussed, it's going to leave our horizon, and then I won't, it'll sort of disappear in this red shifting away. So in the conventional cosmology book, you will hear the description as if all of this really exists, as if it's classical, it goes on forever, there's galaxies off to infinity. In my view, that's just inconsistent with the idea of a quantum theory. So, can't be right. And nobody... There are all sorts of clues. As you know, Planck satellite is giving us some amazing clues. So I feel we're on the threshold of a new revolution in physics, and it's going to be pretty exciting. Right, cosmology in 20 minutes. I'm just going to give you a little sketch, and hopefully I will show you de Sitter space. By the way, our real universe is not de Sitter space. It's de Sitter space in the future, but as far as we know, there was a singularity in the past, which was space-like. So we can't. So the real universe has a singularity. Has a singularity in the past. Okay, let's discuss cosmology. I'll try and just give you a sketch. Now, you've done some of this, right, with Matt Johnson?
Penrose diagrams for Minkowski space.
Did you? You didn't do de Sitter? Pardon?
In one of the tutorials, we looked at
good.
the Penrose diagram for Minkowski space.
Very good. So you didn't do de Sitter. You didn't do de Sitter space. Okay. You see, the other thing about Minkowski space, there's no scale. Minkowski space is no scale, so once you write it down, sort of the only natural scale is infinity. I mean, it's the whole thing. There's no scale in Minkowski space. But in de Sitter space, there's a scale set by the dark energy, the cosmological constant. And that's a very fundamental thing, and I believe that the only theories which really make sense are ones with such a scale. And that scale will define the length scale beyond which classical description breaks down. Okay, so cosmology. Again, we're looking for solutions of the Einstein equations. And the guiding principle, so you're faced with these horrible nonlinear PDEs with many degrees of freedom, and nobody has the faintest clue what the general solution of Einstein equations look like. It's just too hard a problem. So imagine you're Einstein. You want to think about this problem, but it's too arbitrary. And at the time, he knew nothing about the universe. I mean, literally, almost nothing. People thought there was only one galaxy in the universe. Until the mid-1920s, there was a fierce debate between Shapley and someone else. Can't remember. Fierce debate, is there more than one galaxy? Okay? So Einstein's working in 1915. He has no clue what lies beyond our galaxy. But he wants to study the whole universe. Evolution of the universe using general relativity. So what does he do? He assumes a symmetry. The universe is homogeneous and isotropic, okay, to a first approximation. So let's just assume the universe is the same everywhere in space, and it's the same in all directions, about every point in space. That's what homogeneous and isotropic means. And this is usually, this forces the metric into a certain form. Which is very intuitive. It's just this is called the Friedman-Robertson-Walker metric. And basically what it says is that, so I'm not going to prove this, it's not hard to prove, but there is a coordinate system in which the metric takes this form. Okay, so the metric, the existence of the symmetry ensures that there exist coordinates such that the line element takes this form. And where k is a number, the curvature scale, the space curvature scale, or let's say the scale, let's say k equals 1 over length squared, where L is the scale of curvature. Of space. Okay, so this homogeneity and isotropy force the metric to take this form. K can be any number in this equation. The simplest case, if k is 0, in which this is just the flat space metric, okay, in spherical polar coordinates. If k is positive, then space is a sphere of radius, so k greater than 0, then space is a sphere of radius L, and actually the proper radius is A of t times L, because this line element is multiplied by A of t, so that means that all distances are just scaled up with A of t. If k is negative, let's write it down this way. If k equals plus 1 over L squared, if k is minus 1 over L squared, then space is a hyperboloid. The sphere is S3, the hyperboloid is H3. That's a negatively curved space of constant negative curvature of radius. You can call it a radius, A of t, L. Okay, so you have this possibility of positive space curvature or negative space curvature or zero space curvature. And observations seem to indicate that the curvature of space is very nearly 0 for reasons we don't understand. The curvature term in the curvature term in the Einstein equation contributes less than 1%. In fact, part of the motivation of the theory of inflation was to explain that number. But in my view, it never really succeeded in explaining it. Okay, so we take that metric, which is a very, very intuitive thing, right? You're just taking a metric, which in the simplest case is just flat three-dimensional space. You're multiplying it by a squared of t. So as a changes, a is called a scale factor. It's just stretching the space. Okay, so this is a very intuitive picture of what space is doing as the universe evolves in time. So now we can work out the Einstein equations. I need these formulae. So first, we can work out the left-hand side of the Einstein equations just by calculating the Einstein tensor G00. So this turns out to be 3 times A dot over A squared plus K over A squared. A dot over A is defined to be the expansion rate, which is also the Hubble parameter. Okay, it's often called the Hubble constant, H, but that's a terrible name because it's not constant. Okay, A of t is a function of time, and A dot over A is a function of time, and so it's much better to call it the Hubble parameter. That's just the rate at which space is expanding. Okay, so if, in particular, if H is constant, then the scale factor is growing exponentially. Okay, so a constant expansion rate means that the scale factor grows exponentially with time, and that is actually what's happening in the universe today. That's this property of de Sitter space-time. So that's the 0,0 component, and just for completeness, will I? Yes. I will bother, so we can work out the spatial components of the Einstein tensor, and this turns out to be minus A dot squared plus 2AA double dot plus K times gamma ij, where gamma ij dxi dxj is the spatial line element, and so that's the dr squared over 1 minus k r squared plus r squared d omega squared. Okay, so that's the spatial part of the metric is a squared gamma ij. So i.e. g mu nu is equal to minus 1 in the tt direction. And then in these three components, it's a squared gamma ij. And it's 0 everywhere else. Okay, so that's the left-hand side of the Einstein equations. And now let's calculate the right-hand side. So the right-hand side, we just need the right-hand side of Einstein, we need to know T mu nu. So T mu nu is equal to, and we're going to assume a perfect fluid form. And let me write it down and then justify why it's a perfect fluid. So T mu nu for a perfect fluid is P plus rho u mu u nu plus P g mu nu. Now let's see, I can't remember. Have we done this in the course or not? No? Haven't done this. Okay. So we've done a fluid of particles, right? And so that's a sort of an attempt at a microscopic description of what's going on in a fluid. But if you want to describe a fluid like water or air or a large collection of galaxies or dark matter or the vacuum energy, a better description is to say that any fluid, I can sit in the fluid, and this is the local fall velocity of the fluid. Okay, so you take some little element of the fluid and you say it has a fall velocity. Any fluid has to have a density. So that's the energy per unit volume. And P is the pressure. Okay. And then the equations of motion of the fluid. The equations of motion are just d mu t mu nu equals 0. Okay, so those equations of motion are enough to define what happens to the fluid, how it evolves, but these are enough to determine the motion of the fluid, the evolution of the fluid, given, very important, if you are given the equation of state pressure as a function of the density. Why are they enough? You see, if the pressure is a given function of the density, for example, in an ideal gas, pressure is, when you do undergraduate physics, pressure is 1/3 nmv squared. The density is nm, so pressure is 1/3 times the density times v squared, and then one can determine v squared in terms of the temperature of the fluid, and so the pressure and density become related in an ideal gas. We have everything is a function of temperature. Okay, so pressure and density would both be functions of temperature, and then you can express the pressure as a function of the density, and vice versa. So it turns out that this is adequate to describe the background in the universe, the homogeneous isotropic component of the matter. Okay, so this is adequate to describe either the radiation or the dark matter or the dark energy or everything else, and all of those really just depend on this equation of state. They all have different equations of state. So examples. Radiation has pressure equal to 1/3 rho, which is basically a consequence of that formula I mentioned. P equals 1/3 nmv squared, but v squared for radiation is the speed of light. So that's 1. And the 1/3 just comes from averaging the pressure, averaging the motion of the particles in different directions. Cold dark matter, also known as dust. Yeah, I should say it's not the dust which Biceps saw. In GR, there's a technical meaning to dust, which is just kind of particles that follow geodesics and don't interact with each other. But in cosmology, we usually call it cold dark matter, just a collection of particles that don't interact with each other or light, except through gravity. They only interact through gravity. And these ones obey pressure equals 0. Then we have dark energy. Now, dark energy is a special thing. Okay, that's the cosmological constant. That is, in its elementary description, all it is I add to the matter action. Okay, so dark energy, I add, well, let's write it down first. So it's P equals minus rho. Why is that true? Start off from the matter action. It's 1 over, I think I already told you this, integral d for x root minus g minus lambda. Okay, because it's a potential energy, so it's negative if lambda is positive. as seems to be the case in our universe. So just add a constant to the Lagrangian, and that's dark matter. And now when you work out T mu nu, you will get, varying this guy, you're going to find lambda G minus lambda G mu nu, so that T naught naught, which is the energy density, is lambda in these coordinates, FRW coordinates. So you can see from here, if P is minus rho, this term is gone, okay? And the T mu nu is P G mu nu. And so this implies that P equals minus lambda and rho equals lambda. Okay, so lambda is strange stuff. It has negative pressure. Okay, maybe you thought pressure had to be positive. Well, it doesn't. Okay. A good way of thinking about that is negative pressure is really tension. When I have a string or an elastic band and I pull its two ends and I say, what's the pressure exerted by the elastic band on the 2 points that are pulling it? Well, obviously negative, right? So an elastic band behaves like an object with negative pressure. And the dark energy or cosmological is the same kind of stuff. If you try to stretch space, it will try to collapse space. Okay, so at first sight, you think it must be doing the opposite of what we say it does. We say it makes the universe blow up. Okay, but it has negative pressure, so how does that work? Well, it's a very peculiar thing, which I'll show you now. So I think we're done. I may just write down the Friedmann equation. So this is an amazing history. Einstein did this first. He assumed the universe was static, because what else is he going to assume? Friedmann was a young Russian who was in Leningrad at the time, in the Mathematical Institute. And so he said, no, let's allow the metric to depend on time, which with hindsight was an obvious thing to do. And he discovered that the universe would expand or collapse. And he told Einstein, and Einstein said, you must be wrong, makes no sense at all. Okay, but it was perfectly right. Unfortunately, Friedmann then took a flight in a balloon to very high altitude and became sick shortly afterwards and died before the expanding universe was discovered. So there's an amazing history of all this. Let's write down the Friedmann equation. So the Friedmann equation is just G naught naught equals 8 pi G T naught naught. Okay, so that reads A dot over A squared equals 8 pi G over 3. The 3 is from there. And then I have, I'm going to write it the following way. Rho lambda. It's a density in lambda. That's a positive number, which is constant. That's equal to lambda. Okay, I'll call it rho lambda, just to emphasize it's a density. So that's a constant. Bingo, exponential expansion, okay? A dot over A is rho. Rho is constant. The universe expands exponentially. That's de Sitter space for you. But in the real world, there's more than that. There's Cm over A cubed. This is the density of matter. That's ordinary matter like we're made of. It's also cold dark matter. Goes like 1 over A cubed. Then you have radiation, which goes like 1 over A to the 4th. And that'll do. There are other stuff. There's neutrino, which starts out like radiation and ends up like matter. But, and then we have the minus k over a squared, where I just pull that term from the left-hand side and put it on the right-hand side. So this is the curvature term, the space curvature term. Now, so we have this differential equation for a of t, the scale factor of a of t. And it's very easy to see what the general solution of that equation looks like. We just use our old trick of writing this as a kinetic energy minus a potential energy, right? So I write that as a dot squared minus 8 pi g over 3 rho lambda a squared. I'm multiplying through by a squared plus c matter over a plus c radiation over a squared equals minus k. Kinetic energy, potential energy are constant. So in the Friedmann equation, the role of space curvature is like an energy of this particle. If space curvature is negative, if we live in a hyperboloid, this looks like positive energy, okay? So it's clear the particle can kind of escape off to infinity. Let's just draw the potential and we'll see that. So this is V effective of A. V effective of A looks like this, minus A squared. Okay, so that is a term like this. That's the cosmological constant. This is V effective of A versus A. This is minus 1 over A or minus 1 over A squared, so that looks like this. Okay, so we have a particle. K, minus k is the energy. So this level is minus k. If k is positive, what's the particle going to do? Well, I can have trajectories where it just does that, right? So it flies out from a equals 0, and it sails off to a equals infinity. It's basically, you know, like a ball rolling in this hill. And as it sails off to infinity, of course, the potential is becoming more and more negative, so it's going to expand exponentially. A of t will grow exponentially. This particle is just speeding up as it falls off the hill, and A of t grows exponentially. So that's for k negative. K equals 0 is basically the same. That seems to be the universe we live in. It just does this. If k is too positive, the universe would collapse. Or it could bounce. Okay, so this is recollapse or bounce. And of course, A equals 0 is the singularity when A equals 0. Okay, so that's the sort of lightning overview of cosmology. Are there any, I think I've showed you, maybe I promised you de Sitter space. De Sitter is just rho equals rho lambda equals constant. And so A of t is equal to is proportional to E to the ht, where h equals square root of 8 pi g over 3 rho lambda. And so the metric is just minus dt squared plus e to the 2ht times dx squared. It's just a flat universe with the scale factor growing exponentially, driven by the dark energy. Now, why on earth, as I said, the dark energy has negative pressure. Why does it call exponential growth? And that is because in the Einstein equations, it's not just the density that enters in the acceleration, it's also the pressure. The pressure is negative, and this negative pressure has a consequence of causing acceleration of expansion. It's just a strange feature of the Einstein equations. Well, it's a bit of an illusion, to be honest, because when you look at the global structure of de Sitter space, you find that what we've drawn here, this metric only covers half of it, okay? So this metric, here's our de Sitter space, this metric only covers half of it. There's another half of it which is contracting exponentially, okay? So when you have negative pressure, you have a part of space-time contracting exponentially and a part expanding exponentially. Yeah, I mean, if you want an intuitive picture, I think it's difficult to give you one. The way I think about it is that to construct de Sitter space, this negative pressure is repulsive. What I do is I throw the universe in at negative expansion, in contraction, and the negative pressure repels it, and it sails off to infinity again. Okay, but it's a strange thing. And this leads to various consequences. In fact, normally you think if I had a bubble, imagine I had a bubble, some region with negative pressure. Your intuition would be that bubble would collapse, not expand. And in fact, that intuition is correct, okay? So if I take a universe and I make a patch, which is negative pressure, the rest of it may continue to expand, but this negative pressure patch will collapse. It's only if I make the whole universe negative pressure that the whole universe ends up expanding. So it's sort of, it's strange. We don't have good intuition for it. And there may be good reason for that. It may not really make much sense.
If you look at the equations of state, it's pretty obvious. The density remains constant. And that means that if you take the second derivative of A, then it has to be positive, so it's considered an expansion.
Yeah, I mean, that's just a mathematical statement. But the Einstein equations imply that, yes, another way of saying it is that conservation of stress energy looks like, so you can calculate d mu t mu nu equals 0. And it turns out this is just rho dot equals minus 3 a dot over a, p plus rho. So if p is minus rho, then rho is a constant. As the universe expands, the density doesn't change. Now, that's kind of intuitive because, you see, think about a string. Again, my example of negative pressure. The thing about a string is that as I stretch it, I'm doing work. The expansion of the string is doing work on it. Okay, so so an expanding string with negative pressure, necessarily the energy in the string's got to grow. Right? So negative pressure plus expansion means growing energy. And that's what this equation means. You see, if p is minus rho, it's like my string that as space stretches, the rho remains constant. That's a funny thing about the cosmological constant. As space expands, it's the same, right? It's just a constant. So you can double the size of space, and you just have twice as much energy. That's because of the negative pressure, because the expansion is doing work against the negative pressure. Right? So as the space expands, and rho is constant, and then, as Vasudev said, if rho is constant, then somewhere here, we've got, if rho is constant, you get exponential growth. Okay. Any other questions? No? Well, you are rid of me. If you ask me nicely, I might come and give you some talks. Yeah, let me just say it's been really, really fun teaching you. And I think you're a fantastic group of students. And I'm not just saying that. I think the atmosphere is really exceptional this year. And I just encourage you to have lots of fun and don't stress. Okay? And I hope to see all of you doing extremely well in the future. So thanks a lot.